Awesome. Let me know if you see my screen. Thumbs up. Awesome.
Yeah,
cool.
We can see it.
Thank you everyone for joining. This is our very first meetup. Many of us here are somehow involved in deep learning. We are interested in learning more about it. Some of us are pretty new to this field. Some of us are actually more advanced and actually doing this part of their day-to-day job. My role for this meetup and this community was to take lessons learned from each other and also follow a well-structured curriculum, usually from resources like Coursera, Udacity, or Fast.ai, and go through that course step by step and actually learn something new, discuss among each other, even go through some coding exercises and do some interesting applications, so that at the end of the day we have something new in our toolkit. This meetup is very open. If you have any ideas for next sessions on how to structure this differently, happy to hear your thoughts. This is my attempt based on many meetups that I've attended in the past, and I'm trying to take lessons learned from each of those sessions and incorporate them here. So first things first, if you're new to the community, the meetup page is meetup.com Deep Learning Adventures, and our first page is called Chapter 1, and we'll see pretty soon why this is called Chapter 1. For this first session or this first chapter, we'll be using the specialization called TensorFlow in Practice Specialization. If you haven't checked it out, it's in Coursera. It's a 4-course specialization that teaches you about deep learning, and specifically deep learning using TensorFlow. And it has an introduction section, learn a little bit of, at a high level, what does deep learning mean. Then you go towards convolutional neural networks, which I use for image processing, course 2. And later on, you go to natural language processing or NLP, where you work with sequences or text or voice. And then later on, you continue on that path with sequences, time series, not just text, but also think of it like ordered data sets, for example, like stock prices and things like that. For this event, we will start with the very first course, and actually just the beginning of the very first course. But feel free to follow on your own rhythm. Our goal here is not to go for the schedule of Coursera. Coursera has some recommendations, week 1, week 2, week 3, week 4. You can do them on your own pace, and we can discuss them here. I know a few of us are taking this specialization, so based on our availability, we'll be marching forth, but the story is that you don't have to follow the same rhythm. You can go faster than us or slower than us based on your availability. That's it on my high-level understanding of the specialization. David, do you want to say a few things about it?
Yeah, I think you've got it right. And as you say, they consider these to be weeks. You can certainly do them in a much more rapid pace if you have more time. But if you've never taken a Coursera course before, just to make you familiar with what they are, they're basically a series of video instruction that you watch. And then at the end of the week, there's usually a quiz associated with that to see if you understand the material as it was presented. And the great thing about some of these courses like this one is there's also a programming exercise that you go through to get your hands dirty.
Awesome. Cool. So let me actually go over this quick slide deck that I put together just to guide our discussion. So that's the meetup page that we talked about. We have a GitHub repository as well. We plan to post code there. I know Coursera has a honor code that we have to honor. We shouldn't post any code directly as we use it from their weekly exercises, but we can take that as a guidance, and we can modify it, and we can use it to build our own code. And there's nothing wrong with that. We can upload that on our GitHub repository. We also have down here Slack. It's on the meetup page as well. Feel free to join us. We'll be posting updates there, sharing resources, and so forth. This is not a typical meetup. Get ready for a fun game towards the end of this session. If you want, you can do that now. You can simply go to joinmyquiz.com on a new tab, and you can enter a game code. We'll be going through this game in the end, and I'll have the same slide in the very end. But if you go to joinmyquiz.com and enter this code, you'll be on a waiting list. And when I start the game, there's a series of quizzes and questions with some interesting ideas. So very simple. I want to make sure that everybody's engaged and having fun at the same time while we're learning about deep learning. You'll see the slide in about 15 to 20 minutes. Cool. If you're texting me something, let me know. It's kind of hard with Zoom to see if somebody's texting me. So the best way to get my attention is just to simply unmute yourself and speak up. Cool. So if you look at our event page, we talk a little bit about massive open courses, online open courses like Coursera and Udacity and edX and all that. So these are platforms that have been around for many years. And actually, for Coursera, one of the co-founders of it, Andrew Yang, is also a very known lecturer from Stanford and also a very known lecturer in Coursera itself. And he has his own specialization that many of us have taken in the past. But as David explained, it's an online platform. You can take videos online. There are suggested deadlines. Some of them you can reset. Some of them are pretty strict. From what I've seen so far, you can reset deadlines based on your own availability. Coursera has this motivational feature that you can set weekly goals. You can say, I want to study one day a week, 2 days a week, or even 5 days a week, and it will remind you every time you log in. I find that really interesting. But given the outbreak now, everything is online, everybody's remote, so this is a good resource for you to use online. And this specialization that we're taking is based on TensorFlow, and TensorFlow is an open-end, open source, end-to-end open source machine learning platform. It was developed by Google, and now it's an open source project. And over here, I did a Google search basically of trends to see how does TensorFlow, Keras, PyTorch, every time you hear them, you see, okay, which one is most popular? It's almost the same discussion as which is more popular, Python or R. They're both popular, and in this case, all three frameworks are popular. Just pick one that you feel most comfortable with, and most of them support major languages like Python, Java, or C and C++. So it really depends on your programming background, I would say. For special cases, like many of us here are dealing with, for example, like detection on the edge for low battery or low energy devices. There are some minor differences here. I know TensorFlow has a very light version of it that you can deploy on small devices. I'm not sure PyTorch has that yet. So if you're looking for a customized solution, maybe one framework would be better than you. But if you're new to deep learning, or if you have an idea and you just want to check out a new model that, for example, this large companies release, most of them have repositories that you can use. Cool. This is just an attribution to Coursera and deep learning. I'll be using some snapshots from their websites. I want to make sure that all credit is attributed to Coursera and deep learning. This is not my original content, and in each slide, you're usually going to see a source where I got these resources from. Again, this is the Coursera front page, and Deep Learning Now AI is its own company that creates some of the content for Coursera. Cool. So let's talk a little bit about chapter 1, which is the specialization. I call it chapter 1 as an adventure because hopefully we'll be taking more and more chapters as we go through them. But basically, the specialization will allow us to learn more about TensorFlow, this open source machine learning platform, many of its applications, as well as how to build and train neural networks. So neural networks is this new paradigm compared to the traditional programming, where now you're using algorithms to figure out the answers for you instead of you having all the answers beforehand. It can process text, it can process images, it can process audio. Obviously, in the end of the day, all these things to make sense to a computer need to be converted to vectors and and bits and bytes, but it can support many different data sources. You can also do something interesting and creative. Like there's a lot of applications for deep learning where you can do transfer style. You can basically take the style of an image and transfer it to another image, or you can even train a neural network to basically create new content based on a language that it has seen, or create new music based on a rhythm that it has seen before. So you can even do what is called fusion of music styles. So for example, if you like jazz and if you like, let's say, classical music, somehow you want to fuse them together, you can train a neural network to do that. I don't know how that would sound, but maybe that'll be something fun we can try later on. Again, this is a beginner level introduction to deep learning using TensorFlow. If you already know the basics of TensorFlow and you're looking for a more advanced course, there's another course called TensorFlow Data and Deployment Specialization. That one focuses on a more advanced features of TensorFlow and actually how do you deploy this in production, and how do you make it work. Cool. So this is the layout that we described briefly in the beginning. It has 4 courses. We'll be starting today with this introduction to TensorFlow and taking a deeper dive in this new programming paradigm. I hope in next session we can cover the rest of them. David and I know we'll be going a little bit aggressively on this. We'll be trying to do as much content as possible. But again, you can follow your own pace, and you don't have to go by our pace. It's an open environment, so you can, based on your availability, based on your workload, you can adjust that. Awesome. In case you haven't used this product, I just want to mention it. Many of us use Jupyter notebooks. Google supports a hosted version of Jupyter Notebook called Collaboratory. And you can log in for free. You can have an account for free. All you need is a Gmail account. If you go to collab.research.google.com, it's basically Jupyter Notebook on the cloud. You don't have to download anything. You don't have to save anything. Everything is saved in your Google Drive, and you can share that content with others. Awesome. So for this event, we'll be talking about the week 1, the new programming paradigm.
Hey, George, how would you compare that to Anaconda? That kind of thing. Is it just more lightweight?
Yeah, much more lightweight. All the packages that you need, you can do pip install directly in Colab. You can even install specific versions of packages. Let's say you're doing something in TensorFlow 2 point something or Keras 2 point something. You can do that very specifically.
The other one difference I might point out is with Colab, you have access to their GPUs, and their TPUs actually are available through it. So it is hosted, and you get access to some very, very fast processors, depending on their availability.
Okay, thanks. But you have to pip install? It's not just strictly web-based?
It's web-based. Most of the popular deep learning and machine learning packages are already pre-installed. Let's say you want to install something that's already there. You can try and import it. If it says not found, then you just do a pip install.
Okay.
Yeah. Good question. Yes, please ask me more questions as we go by. Yeah, this session is recorded, I guess. Yep. And will be shared once we end the meeting. Cool. All right, so the traditional programming paradigm is that we have data and we have rules. Somehow we combine that data and rules and we come up with answers. And this is an example here on the right. If somehow we have, let's say, a fitness tracking device and we want to measure if somebody is walking, we have access to that device. Let's say if the speed is, let's say, less than 4 miles an hour or less than a metric, we can call the status walking. If somebody is less than that metric, that threshold, but we can say that walking. But if somebody is higher than that, let's say 5 miles per hour, we can say that somebody's running. What happens if you add a little bit more complexity to the model? What happens if you actually use a bike? Then you have to do different cases. And what Lawrence and Andrew, the instructors here in this course, saying, okay, what about if you play a sport, if you play golf or play baseball or soccer? And can you tell if somebody's running or walking or just stretching? Like, what is the rule there? So this traditional programming paradigm here is not enough. Simply, we don't know the rules. We have the data. We have no idea how to code this. It will be a very complicated model that probably, if we try to make it work for golf, if we change some of its parameters, it might not even work as well. So the machine learning paradigm is a pivot on that model, in the sense that instead of getting answers now, we provide answers and data to the model. Basically, we have data, we have labeled data. Our answers are labels, and let the algorithm figure out the rules and how do the answers evolve from the data. So let's use data and answers as input and let the algorithm come up with different rules. So that's the shift in paradigm. So what that means in machine learning is that we provide data, and that could be an image, that could be some kind of a metric that we have on our sensing devices, that just bits and bytes to the algorithm. It doesn't understand what walking is, it doesn't understand what running is, it doesn't understand what biking is. So humans have to label this data. That's why you see a label, and that falls under the supervised learning paradigm. There's another paradigm called unsupervised learning that we won't cover this course. So then we have somebody labeling this data, and we give that as an input to the algorithm, and we train the algorithm basically to tell us, when we give new data that we don't have the label for, unlabeled data, what is the right answer. And the simplest really machine learning start on the simplest machine learning algorithm we can write is basically try to do some kind of mapping between two series. So in this case, the input is x. It's just a series of numbers, -1, 0, 1, 2, 3, 4, just a linear progression here. And the output is a scaled version of it. And if you notice, there's a linear combination of x that gives you y. It's probably 2x minus 1, but the algorithm doesn't know that. So it's our goal to train a network that will basically give us the relationship between x and y. Cool. So if you think of it as from a mathematical perspective, the simplest model I can explain this relationship is a linear model. So that means that we need two parameters. We need a weight and a bias. And over here on the right, I have a plot from another algorithm, not another data set, not this data set. But basically what we want the algorithm to do is figure out a connection between x and y. And in this case, that connection is linear. So in the beginning, we will initialize our network. We'll have some pretty random weights and biases, and the network won't understand what is the relation between x and y. But pretty soon, we'll be able to make some kind of a distinction. And this graph will make sense pretty later on down the course. So speaking of TensorFlow, what is the simplest model we can design for this challenge? There are a few steps that will go in details pretty soon, but for now, let's assume that we have all the necessary packages pre-installed. And again, if you're using Colab, they're already installed. If you're using your own environment, you might have to install TensorFlow and Keras, and we'll go into that in detail. But from just a programming paradigm, what is the simplest model we can do? From Keras, we can import something called sequential. Well, all that says is that it takes as input a list of layers, and those layers will take our input. Our input will pass through each one of these layers step by step until we get an output. And in this case, we only have one layer. It's called a dense layer. All that says is that the input, whatever input we provide to the network, is actually given to all the different neurons of this layer. And this layer has only one unit, or one neuron. That's why you see this unit's 1. Then this is basically our model. It's a very basic one hidden layer, or one layer, one unit network that takes as input just a very basic number. That's the input shape, just a number. In this case, if you remember from previously, it was x. And it's supposed to give us back another number. And then, okay, how do we use this model now? We have to use 2 or 3 functions in this case. The first one, we have to figure out when our model creates an output, how is that output compared to the ideal output? So our model will be given an input, let's say -1. Our model will probably give, let's say, -5. How is that -5 compared to the true label, which is -3? How far are we? So then how far are we? It's a distance metric, and that distance metric here is using something called mean squared error. If you come from a math or statistics background, all that is saying is that you want to take the model output, which is -5, you want to subtract that from -3. So you want to do -3 minus -5. You want to square it, and then you want to do this for all your inputs and outputs. And you want to take the mean value of them. So you want to see basically your output, how far is it from your input. There are different loss functions. This course, I'm pretty sure, will cover them in detail. Based on other courses, this significantly impacts your model, as well as something called convergence that we'll see soon. So that's the first ingredient that we need. The other ingredient that we need is called an optimizer. All that does is, given the loss, it tries to figure out a way to update our weights and biases. In this case, we only have 2 of them. If we have a linear line, the weight and the bias. And this is a way for this algorithm to update the weight and the biases. In this case, we're using something called stochastic gradient descent. There are many other optimizers that you can use. If you remember your calculus background, all this says is that if your loss function is differentiable and if you can take derivatives, if you head towards the negative of your derivative, you'll basically go down a slope, and your goal is to find a minimum value for a slope.
Hey, George?
Yep.
So is it the optimizer that determined that this was going to try to fit to a linear equation, or where in this code did it know to try to fit this to a linear equation?
So that linear equation, the simplest models that couldn't explain it was a linear function. That's from our perspective. From here, based on the number of hidden layers that we're using and the number of hidden units that we're using, it's just 1. All that says behind the scenes is that it will only have 2 parameters. So it's not necessarily trying to find a linear or a nonlinear or a hyperplane function. All it says is that I only have 2 parameters in my disposal to adjust, and I have an input. What kind of combination can I do to make that happen?
I see.
And internally, these networks also have some nonlinearity in them. All of them have something called an activation function. So even if you combine linear combinations of your input, at the end of the day, you always pass them through a nonlinear function that will allow your model to learn.
And George, that is true for almost all cases, except for the dense layer by default. If you don't specify the activation parameter, it defaults to a linear activation.
Got it. Okay, very good.
So, but yeah, almost always you're using a nonlinear activation.
Then we want to quantify, we want to actually measure down our inputs and our outputs. So X is our input, or X's. This is our linear progression here, and it's of type float. This is using a library called NumPy. And our outputs are a scaled version of that. And for us humans, it's easy to see that this is a linear combination, but for the network, this is just a series of numbers. Then we take those X's and Y's and we define our model here. We define a way of how the model detect the difference and how use that difference to update the weights and the biases using the optimizer. Then we use this method called fit. We give the input and the output. We give something called epochs. Epochs is basically how many times is our model allowed to go through our training input, or in this case, this list of numbers. How many times is our model allowed to see that? Once, twice, 3 times, 4 times. Now, for us humans, looking at it once is enough. For a neural network, it actually has to look through it multiple times. And in this course, they decided to go with this very high number. You can try smaller numbers, you'll see different answers, but all that does is updating your weight and bias until you come to a smaller value of loss. You'll never achieve loss of 0, but you'll see, as if you plot the loss function, you'll see that it's minimized and it's going slower and slower and becoming smaller and smaller. Then the output, the final thing that you want to do is you actually want to call a method called predict from your model. You want to give it an input that your model has never seen before, in this case 10. So ideally you expect 2x minus 1, so it would be 19. But based on many parameters that we'll see soon, that might never be the exact answer. Cool, so that was the high level one. These are some screenshots that I took. If you actually try to do this in Colab, so as a reminder, this was the traditional programming paradigm where you actually knew the rules and the data, and you could easily return an answer. In this case, you have data and answers, and you're trying to find this rule or this linear equation here. So in Colab, you can import TensorFlow from in Python from import TensorFlow STF. You can import NumPy as NP. These are just naming conventions. You can name whatever you want, but everybody best practice follows this shortcuts. And then from TensorFlow, you can import something called Keras. Keras is a higher level API, sits on top of TensorFlow. That gives you a little bit of easier readability and user flexibility compared to TensorFlow. If you want to look at different versions of what versions of these packages you're running, usually if you do that model dot _ version _ you'll see that version. So if you write a model that was, let's say, in a previous version or in a specific version and you want to use that, there's a way for you to tell Colab, please use the specific version. And then this is the same model that we defined above. And TensorFlow has this method called summary. It'll actually give you an overview of your model. In this case, it only has one layer because you see only one row here. It takes as input one number. And right now we haven't specified the output, but that means that we expect one number basically. And these parameters here that you saw, that I mentioned in the backend, that actually too, because you have a weight parameter and a bias parameter that are combined through a linear equation. So your output would be a linear combination of your input. By default, as David mentioned, this will be passed through a linear function or ReLU, and then you get your output. So your total parameters are 2. How many of them can you change or train based on that optimizer function that we saw? 2. How many of them are static? 0. So you're allowed to change 2 variables and somehow find a relationship between x and y. This is the same code that we saw before, the optimizer and the loss function, and the same input and output. And if you actually try to run this in Colab, if you call the method fit, you don't have to run it for that many epochs. I tried running it for 10, 20, 100. You'll see that it will tell you how long did it take for your model to be trained for each epoch, meaning seeing the entire data, and what is the current loss. And as you train this for more and more epochs, you'll see this loss function dropping. And at the end of the day, you'll see, let's say, if you train it for 300 epochs, you'll have some value very small. And what you really want to do is call the method predict, and you'll get something that is close to 19, but not exactly 19. And this is an interesting question, like, how come this didn't give us the right answer? So then there's a discussion in the course, if you take the course, of, I think, 2 things happening. One is your model is basically a probabilistic model. It's not a mathematical model in terms of exact answers. All the predict method that you're calling here is actually giving you a probabilistic an output based on probabilities, number 1. Number 2 is based on your data availability and how much data you have and how complex is your models. We had a series of 6, 7 numbers, so that's not a lot of data. And our model wasn't the most complicated. It was just a very simple line. So ideally that should have been enough. But for those two reasons, not a lot of data. And also this is a probabilistic model. You'll never, not never, but you're never going to get the exact 19.0. Is that your understanding as well, David?
Yes, that was the two that he pointed out, and it makes sense. Yeah.
Cool. Any questions so far?
I was just, for people that knew, George talked about the Y as being known as the labels. The X are sometimes referred as features. You might hear people use that lingua. Mm-hmm. Features and labels.
Awesome. Cool. Then the week one of this course concludes with some references. There's an introductory course to AI called AI for Everyone. I highly encourage, if AI is pretty new to you, to check it out. It gives a very high-level explanation of what is AI and what can it do and what are its limitations.
Sorry, I have one more question, if I may. When you were describing at the end the model, you mentioned some parameters that wouldn't be trained. Can you elaborate on what those would be? I mean, I know we don't have anything in this case, but can you give an example?
Yeah. So when you do this model.summary, you will see the number of parameters that are hidden behind this, this single neuron. And the single neuron accepts a single number. The input shape is 1. It's only one neuron. The unit is number 1. And what that does is each neuron in a neural network has two things: has a weight associated with whatever input it's getting from, and also has a bias. So weight is, think of it as how much can I scale my input? Can I scale it by 2, by 3? Can I multiply it by 4, by 5? That's the scaling factor, the weight. The bias is after I multiply it, think of it as a DC level. How much can I increase it or decrease it? +1, -1. So think of it as your output Y here in the traditional programming paradigm will be a trainable parameter W, your weight, times your input, plus a bias, B. So then what this model would do is it would adjust the weight and the bias so that your output is closer to the true output as it goes through your data.
Correct. So what would be a non-trainable parameter? That's my question.
Hey, George, I think if I recall, in like a convolutional neural network example, you might have some offsets or some padding or some step sizes that might not be trainable parameters. They might just be fixed. Is that an example of a not trainable parameter, or is that a hyperparameter?
Yeah, no, that would be something that you don't train. I'm trying to think of something at this level.
Yeah, it's probably, I think you're thinking, George, that later on you might hear about what are called a concept called transfer learning. Mm-hmm. And there are many models out there that have been trained on gigantic data sets, and you may want to take advantage of that, but you don't have the ability to train on a gigantic data set for weeks and weeks. So you can inherit the weights already pre-trained for that model and set them to not, you can change the settings so that they're not trainable. Mm-hmm. And you may only train a few extra layers that you add to that model.
Okay, that makes sense. Thank you. Thank you.
Yeah.
Awesome. I have a question. Let me know if I'm knocking you off your timing. You know, we can move on.
No, we have time.
But I don't understand. I understand neural nets to a reasonable degree, and I still don't understand why a bias is important and is seemingly essential. You know, because it shows up everywhere. So I guess that's it.
Got it. So if you think at it from a mathematical perspective, let me go back to my image of describing, let's say your input and output are linearly correlated or linearly dependent. That means that there's some kind of linear combinations of input that gives me my output. if you're only allowed to scale the input, let's say x could be wx, could be 1x, 2x, 3x, minus 2x, that will give you the direction of the line, but that wouldn't give you the flexibility to move the line up and down. So that's just another flexibility advantage you can take basically when you have two parameters. If this network was only allowed to use only one parameter, probably you wouldn't find the right answer. That's one explanation. Anybody has a better explanation?
Like in this linear case, you wouldn't always want to have to go through the origin here at 0, 0. In this case, you're going through the origin offset by 1, I guess, which is your bias.
So the other thing I was going to say is, as an example, in the example that you're using, if we weren't using a probabilistic system, your weight would be 2 and your bias would be -1.
Correct. Correct, yeah. That's the, I mean, this is an artificial example, but that's the relationship between this x and this y vector.
Right, so the neural net is basically training to get as close as 2 for the weight and -1 for the bias as possible.
Correct. Yep, correct. And the good thing is you actually can look at the weights and the biases and you can see how, what's their value. Maybe I can do that in our next time, but you can actually see the weights and the biases in your network.
If you did not use a bias in a neural network, which is conceivable to me, you would just have the regular structure with the weights and the inputs, but without a bias. Do you inherently get a worse result than if you use a bias?
Yeah, I would say so. Yeah, absolutely. If you're not allowed to use a bias, let's say your output is a biased version of your input, you're never going to guess it. You'll never be able to train a network that achieves high accuracy.
Okay. All right. Thank you.
Yep. Good questions. I'll take notes for the weight and the biases. Maybe I can add them next time. A better explanation. Cool.
It's interesting. I guess if you think about it, the bias is just moving where you're interacting with your activation function. So if you have no bias, then your expectation should be 0 for your output. The bias is almost like the expectation of the linear portion of the calculation, assuming that your expectation on the previous layer is 0 anyway.
Yeah, I was going to say, if you basically didn't have any bias, for an input of x of 0, you would always have y of 0. Always.
Right.
Okay, I have to ponder that one. So in other words, the bias is moving. Is that what you're saying? As the weights adjust, the bias will move that intercept.
Yep, exactly. The bias is a trainable parameter, so the intercept will change.
Okay. All right. Thank you.
Yeah.
Right. So I don't know what background we're assuming for this discussion, but if you assume that a sigmoid is your activation function and you have a large bias, what you're doing is kind of moving your distribution to go towards the flatter part of that sigmoid. Whereas if your bias is close to 0, you're more likely in the linear portion where the function is quickly varying. But it's a really interesting question. I never really thought about the impact of, if you didn't have a bias.
Awesome. Any other questions? I have a few more slides left. Cool. There is a...
Yes, I'm sorry. Maybe you could probably do this at the end, but I joined sort of late, and yeah, and I know this is the first session. I just was hoping to get like a 30-second overview on what we were covering. I actually thought we were going to be looking at the book Deep Learning. But yeah, if somebody can just give me a synopsis at some point, that'd be helpful. Thank you.
Sure, yeah. So if you go through our slides in the very beginning, we have some introductory section there. We talk about the specialization called TensorFlow in practice. That assumes a little bit of a knowledge of deep learning, but
Okay.
we're happy to go, through some of the basic concepts, perhaps.
Thank you. Yep. I appreciate it.
So there's a GitHub repository for this course. Lawrence Maroney has it here. I have a link on the slides, and it has the same code that we saw before. And this is the other course that I mentioned, the AI for Everyone. If you want a very basic beginner level introduction to AI, this would be a very good first start. Another resource, some other resources that the course refers to is, if you're a little bit more advanced, something called TensorFlow Summit. That's actually an online event that happened in March. It was completely online. It introduces new features in TensorFlow that you can watch on YouTube, and I have links here. Something else that maybe can be answered by another resource that can answer some of our questions. TensorFlow has this playground.tensorflow.org resource that you can basically play around with a number of inputs. How many hidden layers you have here? In our case, we only have one input, one hidden layer, one neuron, and one output. So it's a very basic 1-1-1 block. And if your data is shaped in a specific way, you can play with that. You can choose how your data is shaped. Is it either linearly correlated or non-linearly correlated? In this case, you can see this is a non-linear correlation between X and Y. And you have labels, let's say blue and orange. You want to find what parameters can you find. In this case, will be more than 2 parameters because you're using more than 2 neurons, more than 1 neuron. But basically, how can I find a mapping function that takes inputs, let's say coordinates X, Y, and gives me the color? If my X, Y, and color distribution is like this. So you can play with this. You can play with the different parameters here. I would recommend you start with the simplest model. 2 input. You need 2 input because it's a 2-dimensional model. Start with 1 neuron and 1 output and see where that gets you. And some other events and meetups in the area that I want to call out. Coursera has this new specialization called AI for Medicine starting soon. I think sometime in April. Check it out. I have a link here on YouTube. There were some other events throughout the week that many of us are part of. I just want to mention them. There's this one on NLP. I haven't been able to watch the recording yet. If anybody was able to attend it or can give us, like a few sentence description, feel free to jump in. I know the Bethesda meetup by very often Marcus is pretty active. It's always packed at least whenever we used to attend it in person. Now it's online. They also had an interesting session last time with federated learning, I think. So how to use smaller devices like edge devices to actually do training of your network and combine that training together to a central model that can learn from all these edge devices. There's another meetup called Nova Deep Learning. That was yesterday, and I actually had a session there which is similar to this one, but it's actually using PyTorch, and there's a recording there as well that is posted. And finally, another meetup that it's a little bit more advanced. It goes through papers for machine learning and deep learning. It's machine learning papers, and I have a link here. Yesterday we had a session on a paper called Attention All You Need. It's a transformer architecture that is used by a lot of modern NLP models. And I just want to also mention that TensorFlow now has a certificate. So ideally, if you take this course and probably the next one, the data and pipelines, I think we should be in good shape to take this certificate. It's pretty new. It was introduced a couple of weeks ago. I have a link here. As well as, if you're aware of NVIDIA's GTC conference, they have an online event that is still going on. I think it's still going on. I was able to take one of their workshops, and it was online, obviously, and covered image segmentation, word generation, and actually something pretty cool where you combine now, you have images and captions, and how do you train a network to just look at images and generate captions.
Is the group with Kathleen and Puneet, is that still going? I know you were part of that.
Yeah, that was going on. That group is focused more, I would say, on in-person communication. That's actually one of the reasons why I wanted to have a separate meetup altogether, so we wouldn't have to be bound by that. But yeah, that's still going on. Last time
They just didn't want to move online. Is that what you mean?
yeah, that's
okay.
Right. That's right.
Thank you.
Yep. But they have a Slack channel. Yeah, we have many of us are part of that meetup, and we talk on Slack there. Cool. Any more questions before we go to the fun part? Awesome. All right. If you're in front of your computer, you can even do this from your phone, but I think it'll be more fun if you're in front of your computer. If you go to joinmyquiz.com, you'll see a section where it says enter game code. And if you enter the code 432236, you'll get this screen here on the right. Just enter your name, some name that we can later refer to. It doesn't have to be your full name. You can just put your initial and click on Start Game. Oh, I hear a lot of bubbles. That means a lot of people are joining. And this is my last slide, question discussions. I can get to that in the end, but this is from deep learning specialization that maybe can answer some of our weights and biases questions. I'll minimize my presentation. I will go to the game. Oh, I see a lot of people join already. Charles, Robert, Ray, Melissa, awesome. I'll give one more minute to everybody else. Again, joinmyquiz.com, 432236. Oh, a few more people joining. There you go. There you go. And we will start in 5, 4, 3, 2, 1, start. I'll actually take the quiz with you so we can see. Awesome. Almost there. If you finish all questions, you might get a redemption question, what it's called, in case you got it wrong. The game will allow you to take again the wrong question, so give you a chance to redeem yourself. Awesome, Jeff, David, Ray, Frank, Mark, Melissa, Chuba, nice. Katie. Wait for a few more minutes for everybody to finish their quizzes. Four, three, two, 6. Awesome. A few more seconds for Chuba, PL. Awesome. And about 10 seconds, I'm going to stop the game. Awesome. Let me pause it. Awesome. Jeff, David, Ray, great job. Congratulations to everyone. I hope you like this game. Curious to hear your feedback. What did you think of the questions?
It was kind of fun.
That was really good. Did you make up all the questions?
I made up all the questions, yeah. I was trying to come up with the questions. Many of them were based on the first quiz of the course, but I modified them a little bit.
I think yeah. Cool. Well done, George.
Yeah, so maybe we can go quickly through them in case you're looking for the answers. Yeah, obviously you figure out the name, Deep Learning Adventures. Introducing programming, use rules and data. What is the output? The output is answers. In machine learning, the output is rules. And how do you import TensorFlow? How do you import TensorFlow STF? How do you import NumPy? This one might make sense after you watch the recording, in case all these concepts are new to you, but import NumPy SMP. So now that you're an expert in imports, how about Keras? From TensorFlow import Keras. The sequential one, remember that was basically a series of layers or a stack of layers. A dense is basically a fully connected layer. Well, I have the last slide, maybe that will answer some of our questions. The loss function compares the output of our model with the label and tells us how far we are. So that would be, it measures how good our current model output is. The optimizer has one job, and that is to give us new and improved guesses based on something called gradient descent. And then conversion is basically a process where your loss function significantly drops and you come closer and closer to the true labeled answers. And then the fit does all this training for you. It tries to map your x's to your y's. Cool. Let me go back to my slide. Present. So this slide is from the Deep Learning Specialization from Andrew Engs, and it's a reference slide that I use. I really like to use for any deep learning course. It's in the presentation. You can take a look at it. There's a little bit of notation here that this TensorFlow in practice doesn't necessarily follow, but in my mind, it makes perfect sense. So here, this is a very typical deep learning network, you have your inputs, or what are called features. As David mentioned, you have 4 features here. In our very simple network, we only had 1 feature, X. Think of it as maybe coordinates and something else, color, weight, or something else. Then those are 4 inputs. They get mapped fully connected. That's the fully connected part. They get mapped to 3 neurons on a hidden layer. And you see this mapping here. So that means that, for example, if you look at this neuron here, it will accept 4 inputs, 1 for each feature. Each one of them will have its own weight, but the neuron itself will only have 1 bias. You won't have 4 biases. You will only have 1 bias. Same with this neuron, it will have 4 weights that it will scale the inputs, and it will have 1 bias. This will have 4 weights, 1 bias. This will have 3 weights because it's only accepting 3 inputs and 1 bias, and that will give it the final output Y. I have some functions here on different activation functions. Maybe we can go that next time, but the most popular one is the ReLU activation function. I don't have it here. There's other nonlinear activation functions as well that work pretty well, and these are some examples of cost functions. Awesome. I don't want to dwell too much into this. I meant this to be a very introductory level. And this is now open for discussion. And what do you think, and how can we tweak this to follow the specialization, but also try to answer your questions as much as we can?
Can I mention something a little bit off topic? It's a special request.
Sure.
So I was in the Transformer paper group last night.
Mm-hmm.
And it was fascinating. And I see there are a couple of folks. I see George and Melissa, and I think David, Mr. Patton.
Yeah.
But it was a little bit out of my, and I was wondering if any of you would like to do a private tutorial session with me sometime, and maybe we could schedule something to go over. Because my understanding is that that's really cutting state-of-the-art stuff, and I've spent a good amount of time today kind of going over it. So you can contact me offline or on the Slack thing if any of you want to do that.
Yeah. I have an understanding of transformers. It took me about a couple of weeks to get there. There are some good resources online that I had to reference to all the time, especially by Jelamar. There's a blog that tries to explain to you what actually happens inside a transformer network. It has quite a significant learning curve. It comes with some understanding of something called attention model that builds upon, and it has a little bit of a prerequisite basically, but I'm happy to share my thoughts with you.
Okay. Would you say I should spend time on recurrence and LSTM before trying to delve more deeply into attention and transformers, or just skip that?
Say it again, Martin.
It seems to be transformers is an improvement over recurrence and LSTM models, and you know what I mean by that?
Yeah, I know what you mean by that.
I'm not particularly strong on those ones either. So should I spend some time on that before trying to move on to transformers, or can you just kind of jump over? The parallelization aspect seemed to be the key thing to it. So
there are a few papers a lot of papers that attentional unit refers to. For sure, you need the original or the third attention paper, which it's called machine translation, that jointly translates and aligns. For sure, you need some kind of a attention background. This one just takes it to the next level.
Okay. Thanks.
Sure. Anybody else? Questions, feedback? The floor is open. David, what do you think we should cover in our next session, or I should prepare for next session?
I think we continue on with the course as you're going through. It's very nice way to cover it. And it'd be great if other people who are going to meetings that we aren't might give us some feedback on some other good meetings or resources they found online, recorded sessions and such. We'd love to hear that.
Yeah.
In the Slack channel or on the meetup page.
Hi, this is Charles Stockman. Can you hear me?
Yes.
Good. I just got a suggestion. When Mark was talking about what should he learn about that specific neural net, would it be a good idea, and I'm not sure about this, would it be a good idea to have a map of how to learn neural nets, what to learn first, what to, stuff like the neural nets, and then auxiliary stuff like maybe statistics and stuff like that. They're important to neural nets. Kind of like a map of how you would learn it. Learn neural nets.
Yeah.
Or learn TensorFlow.
So there's quite a few resources there. Yeah. The most popular one that many of us have taken, it's a deep learning specialization from Coursera again. That's on the same platform. Fast.ai has their own courses as well. They follow something called a top-down approach, where you actually code something without really understanding what it is. Then later on, they explain to you what is a dense layer, what is a sequential module, what is a fit. But you actually first start coding. I don't know if that's the best resource for everybody. Udacity has very good courses as well, and I know now they're giving a month for free for most of their courses.
I'm not talking about a course. I'm talking about just an idea of how you would approach learning neural nets. What would you learn first? That kind of thing.
George, I think he's asking for like a roadmap.
Exactly.
Yeah.
Mark had brought it up, and I thought it was a pretty good idea. It just might come in useful for people.
If I could for just a minute, I'm not sure I have a complete roadmap, but you definitely need a background in I would say in a certain amount of math, and I was very rusty on a lot of it. There is a Coursera course stuff on, I think it's called Mathematics for Machine Learning, and it offers you like 3 things, and it will point you to kind of the thing, if you don't want to do the course, at least it'll point you at some of the things that you need to know about. And I think the first one was linear algebra, so dot products and all that stuff, and cosine similarities and things like that. And then there are a couple of other, maybe calculus, for that as it pertains to backprop. And then there's another one, I forget what that, more statistical kind of things. But if you want to look that one up, that specialization on Coursera, I'd suggest it's pretty easy, but it's a good introduction.
Yeah, but for sure you need some basic linear algebra, Charles, and if you code this, you need some coding background as well. But linear algebra, some calculus would be useful, especially when you talk about derivatives and optimization functions. Anything else, Melissa or David?
Yeah, actually, I didn't understand exactly what we were going to cover today. I think this is a really good format, and I like the pace. So for whenever the next meeting is the best course of action to prepare is to try to do is it week 2 that you'll be doing, or was this the whole first class course in specialization?
I would be a little bit more aggressive. I know David and I will probably be finished by the first course in just a week. We were thinking of finishing all 4 or 5 courses in just a month, but that's because we have including you, we have a background in it. If people are interested in doing a slower version of it, we could. We need some help, pacing it and also putting these resources together. I'm happy to do it. I need some help. To be honest.
Well, okay, so let me rephrase then. How soon do you think you'll be doing the next course? It seems like I can't tell, but I'm not sure if you did week 1 or if you did course 1 tonight, because I haven't done it.
Course 1, week 1.
Okay. So the next one, you think a few weeks worth? Maybe you'll post it.
Week 2, week 3, week 4 of course 1. Yeah. Next one, we probably can cover the entire course one.
Okay, cool. Thanks.
So if you want to prepare, if you want to take a look, please enroll. Is that a too aggressive pace, David? What do you think?
You're talking about doing 1 week every time we meet?
No,
Like the next one will cover week 2?
I was thinking next week would cover week 2, 3, and 4.
Oh, all of them. Okay.
Or is it too much?
We could try it and see, and if nobody can keep up, or if you can't fit the material into a thing, then we could always like take it down a notch.
Yeah.
How often are you proposing we meet, though? That would be quite a bit.
I'm open to suggestions.
Okay.
What works for you? This is an open floor, everyone. Weekly?
I wouldn't mind a couple of times a month or every other week or something.
Couple of times per month.
Okay.
Yeah, I like at least once a week is good.
Yeah.
I could try for that.
All right.
Okay, so we know it's once a week. Now that we have to figure out how much do we cover in a week.
Are we looking at Fridays for the most part?
I'm open to that. We just put Friday because we literally got the idea of starting this meetup on Monday.
All the days are blending together to me now.
Yeah.
So my suggestion maybe is, I'll just throw this out there. If we're going to meet weekly, that we go through a single week of the course every week. I suspect as more people join in looking through the course or auditing it or taking the course, there'll be a lot more questions generated, but yeah, it's just a guess.
Got it. Okay, that's a good suggestion. We can do that weekly, and we only cover 1 week of the course, regardless of where we are in our own progress. Okay, we can try that for the next one and see how it goes.
Has anybody done week 2 already?
No,
I haven't even looked up for week 1, so.
Yeah, I didn't know we were going to be doing this.
Sure, that's fine. I just wondered if anybody had, we could get a gauge as is the content, does it become harder, and do we slow down, or is it stay at this level? I'm not sure.
I didn't know. Thanks for even pointing me to this this course. I didn't know it existed until I saw your invite, but I'm totally in for jumping in at a fast pace for this as well.
Okay. Just to give an idea to people, David, how long did it take you to actually finish week 1 of course 1?
It was about 2 hours.
2 hours. I'm assuming that will change over time, but the very first week, the very first course is very simple, just a couple of hours of videos and exercises.
I suspect the exercises will begin to take more time in the following weeks.
We can be optimistic. We can, I can put 2 weeks together or 3 weeks together, and we can see how much we cover in an hour. We're already 15 minutes past an hour, and we stop there. We don't have to find that solution right now.
I think that's good.
All right. Next Friday works for everybody, or Monday, or any other day of the week or weekend, if you prefer.
Friday's good.
Okay. Thumbs up or smiles. It's hard to tell when you don't have a video. Okay, I'll keep it on Friday then. 7:30 works for everybody. Oh, I like the. Oh, you can do thumbs up. Cool. Okay, awesome. Cool. Okay, I'll stop recording here.